Hello, I'm Vladimir Cardenas, and I'm presenting a Teach One topic for the problem with code assignment of the course HAP 671, Healthcare Databases at George Mason University. Well, I'm not only interested in showing you my recommended approach and thought processes for this assignment, I am also looking forward to hearing from you on alternative approaches that you can come up with in the discussion section. And so let's begin. For this problem, we need to help our colleague address some issues he is facing with his SQL code. He needs to query 22 different antipsychotic medications across 4 columns from 2 different tables of a huge database. Unfortunately, the dataset is so huge that every time he runs the query, the server crashes. A snippet of the SQL code is shown on the right. The query shows several opportunities for optimization, some of which we can discuss in the succeeding slides. From the SQL query provided with the assignment, we can assume that indexing was not enabled. By enabling indexes of key columns, we can optimize the search process. The columns that we should create indexes for are those that were used in join and where clauses. By doing this, these indexes will make the execution of these clauses more efficient. Using this knowledge, the following columns need to be indexed. First, the local drug SID columns from both the RxOut table and the local drug table, which were used for the join clause. The release date time and the local drug name dose columns from the RxOut table also need to be indexed because they were used in where clauses. And finally, the drug names columns from the local drug table, which are local drug name with dose, pharmacy orderable item, and national drug name with dose, also need to be indexed because they were used in where clauses. It should be noted though that although indexing is a necessary step for further optimization steps, they do come with drawbacks. First, the initial creation of indexes can be resource intensive. Second, although indexes optimize read processes, write and update processes will take longer. This is due to additional maintenance required by the SQL server. After creating the indexes, we can now explore optimizing the SQL queries themselves. The initial query utilizes temporary tables, and although temporary tables are optimized for some applications, they do consume memory. If the dataset is large enough, the server may end up running out of memory and crash because of this. Using database tables that are using server storage instead of memory can help address this. And although there's a penalty that storage is slower than memory, by preventing the server from crashing, we help ensure that the query is completed successfully. It does not stop in the middle. A sample query to create this database table is shown on the right. Here we use the database table dbo.depthfill in place of the temporary table #depthfill. We also use smaller data types for text. We use nvarchar 255 instead of nvarchar max to further optimize resource utilization. In fact, by selecting data types that are appropriate for the size of the data, you will be able to further optimize this table. For example, we can use smaller forms of nvarchar. We can use tinyint, or we can use smaller data types if the data allows for it. Next, we can then explore breaking down the huge query that the analyst originally did into smaller queries. The approach that I am recommending queries one medication type at a time. The results of each of these small queries can then be appended into the database table that we created, dbo.depthfill. By breaking down the query this way, we can reduce the number of OR statements that the query needs to process from 88 in the original huge query to only 4 for each execution of the smaller queries. We can thus reduce resource utilization and execution time of retrieving data for each medication type. As an additional benefit, this approach allows for partial runs and having partial results. This will allow the analyst to split the work across multiple sittings and not wait for the entire query to execute every single time. The sample SQL query to apply this approach for 2 medication types, amitriptyline and clomipramine, are shown on the right. And this query can be expanded for the other 20 medication types that the analyst is interested on. There will be times though that the data set will be so huge that even after applying the methods that we explored earlier, we still need to do further optimization. Another approach that we can explore is to break down the dataset into smaller batches to manage the server utilization further. Selection of the optimal batch size will ultimately depend on the structure of the data and server capabilities. That being said, for this exercise, we can explore breaking down the data into time periods of 1 year. The sample SQL query on the right show how to apply this approach for the latest 3 years of the data for one of the medication, amitriptyline. The query can then be expanded to all time periods or years and for all other medication types. I would like to note though that these recommended strategies, indexing, using database tables, creating smaller queries, and creating smaller batches from the data, should be applied with caution. Because ultimately, it is the underlying structure of the data, the size of the dataset, and the capabilities of the server that will dictate which optimization approaches we should use. We need to extensively test these approaches and address any issues that may arise to find the solution that will actually work with our data. Furthermore, we should consider future scalability in our solutions in case we require additional data or analysis later on. And that is a wrap. I thank you so much for listening. Again, I am interested to know what you think of these approaches, as well as any alternative approaches that you might have. Feel free to post in the discussion section or reach out to me through my email so we can discuss and learn from each other. Have a great day.